Hello guys, in this video we will talk about learning curves and how we can use them to analyze our model. A learning curve is a plot of model learning performance over experience of time. Learning curves are widely used diagnostic tool in machine learning for algorithms that learn from training dataset incrementally. The model can be evaluated on the training dataset and on a validation dataset after each updated during training. And the plots of measured performance can be created to show learning curves. Reviewing learning curves of models during training can be used to diagnose problems with learning, such as underfit or overfit model, as well as whether the training and validation datasets are suitably representative. During the training of machine learning model, the current state of the model at each step of the training algorithm can be evaluated on the training dataset to give an idea of how well the model is learning. It can also be evaluated on a validation dataset. Evaluation on the validation dataset gives an idea of how well the model is generalizing. We will take a closer look at the various cases that the learning curves might be. The example will assume that we are looking at a maximizing metric, meaning that bigger relative scores on the y-axis indicates more or better learning. Now let's start with underfitting learning curves. Underfitting occurs when the model is not able to obtain a high score on the training set. First, we will import the libraries and the dataset. And here is a code to plot our train and validation scores over our training examples. So in our example, we have a digit dataset and Gaussian naive Bayes classifier. And after fitting the data, our learning curves look like this. This is the first possible underfitting curve, which occurs when the training score will decrease, but the validation score will increase. This indicates that the model is capable of further learning and possible further improvements, and that the training process was halted prematurely. We can fix this by providing more data to our classifier. Now let's try SPC classifier on the same data, and let's see the learning curves of this model. This is the second possible underfitting curve, where the training curve is at fixed high score and the validation curve is at fixed low score. This happens when the model does not have a suitable capacity for the complexity of the dataset. This can be fixed by using more complex classifier or by changing the parameters of our classifier. Now let's talk about overfitting learning curves. Overfitting refers to a model that has learned the training dataset too well, including the noise. The problem with overfitting is that the more specified the model becomes to training data, the less well it is able to generalize to new data, resulting in an increase in generalization error. This increase in generalization error can be measured by the performance of the model on the validation dataset. This often occurs if the model has more capacity than is required for the problem, and it can also occur if the model is trained for too long. Now let's use decision tree, which is a more complex model. We will set the max depth parameter to 100 and apply cross validation, but by setting a very small testing set. And let's see what happened now. The plot of learning curves shows overfitting because the training score is relatively high, while the validation score increases to a point and begins to decrease again. The inflection point in validation score might be the point at which training could be halted. So to prevent overfitting, we can change the parameter values of our model. For example, we can change max depth to 5, or we can choose a simpler classifier. Also, we can give the test set a bigger fraction of our data. Now let's talk about a good fit learning curve. A good fit is the goal of the learning algorithm and exists between an overfit and underfit model. A good fit is identified by a training and validation score that increases to a point of stability with a minimal gap between the two final scores values. The score of the model will almost always be higher on the training dataset than the validation dataset. This means that we should expect some gap between the train and validation score learning curves. This gap is referred to as the generalization gap. Now we will apply cross-validation and set the test set to 20% and classify our data using SVC, having a gamma parameter of 0.001. The plot of learning curves shows a good fit because the plot of training score is high and the plot of validation score increases to a point of stability and has a small gap with the training score. You should keep in mind that continued training of a good fit will likely lead to an overfit. So that's it for today's video, and see you in the next one.